Welcome back. All right, so this is getting ready for calculus. So it's the last set of videos that I'm going to make with regards to kind of high school math, at least. I'm sure there's going to be many more that I'll probably make. But when you are starting calculus, so this is most likely in grade 12, maybe grade 11. And at that particular point, you might want to think about how you want to be able to enter calculus in terms of preparation. So this video is not going to be meant for providing you a huge amount of content. It is more about trying to give you the foundational items that you should be comfortable with from your functions courses. So either from grade 11 functions, or possibly if you've done advanced functions in grade 12 or something similar. So the ultimate beginning in calculus is all about understanding slopes. Now, slopes in general, you have started way back, possibly even in elementary school, but definitely in grade 9 and onwards. So those slopes are always dependent. So you have a rise, okay, and a run. You understand that there's an independent variable, there's a dependent variable. And once you understand that concept of the slope, then at some particular point, you should have tied in slope to rates of change. Now, the rates of change that you're going to be running into, you should understand it from the viewpoint of kind of real life of what happens. What do these rates of change actually mean, so that you're not just thinking about X and Y or whatever variables you're using. Try to think about it intuitively. Okay? Now, those rates of change that you have are going to be starting to be applied to functions, so to your functions courses. So how you define your functions, you can see here on the screen, f of x, v of n, e of t, whatever. It doesn't matter, okay, how your functions are actually defined, but you should have a comfortable understanding of a function, seeing it, what it means, okay, and then you slowly will begin, okay, talking about average rates of change, which really, from the viewpoint of a function, is nothing else but understanding secants. So what are these secants? How do I calculate the actual secant line? Can I put restrictions on that, okay, or not? And then from secants, what you slowly start diving into is into instantaneous rates of change. And those are just tangents at a particular point of a function. Now, because you're starting calculus, the items that you'll have, okay, especially in the beginning, are not going to be, too crazy. They will be something that you should be able to understand. So those are the things that you should really prepare yourself for. Now, what I recommend every student, so please don't be lazy, go over these items and then refresh your mind from, okay, your study in functions, okay, of these. So what is a secant? What is a tangent? Because you're going to need it pretty heavily, all right, okay, throughout calculus. So let's dive into some of these concepts. I'm going to give you an overview. And if you really will want to know, okay, I'm going to put a playlist together from the functions course, okay, that will have just several videos introducing you to all of these topics. If you have forgotten them and if you want to have a really solid foundation of it, at least some intuition, I'll put up a link up above there, okay, with regards to that playlist. And then, of course, you can find the entire kind of item with regards to functions on the site that I run. Okay, so you're probably going to see that. I'll put up, okay, a view there. So that's 1mjourney.com. Go to click on the math button and then scroll down to functions, in particular advanced functions. Okay, and then you're going to see, okay, so right there, okay, so there's one particular chapter that I would want you to look at, and I've included it right in that getting ready for calculus chapter number 1. Okay, so first off, for us, rates of change, okay, and this idea of a slope. So let's think about that. Let's go back to that idea. So with regards to rates of change, so I've written numerous things here because I wanted to tie it into real life. Okay, now when you are talking about a slope, I hope that all students will know, okay, that a slope is nothing else. Now we have given it, the designation of m, but really it is the change of your y variable, okay, with respect to the change of your x variable, where your y variable is the dependent variable. So that will be on your vertical axis. And then your x variable is the independent variable. And it was nothing else but simply the idea that you would have if you would plot 2 points, doesn't matter where those 2 points are. So let's imagine, okay, so this is point number 1, x1, y1, it will have some value. This will be a point which is going to be x2, y2. How you label them doesn't matter, but if you want to find the slope, all right, okay, between here, then it is nothing else but simply just finding the rise. Okay, so that is the rise, so going in this direction, okay, and then this is the run that we have, and that is what our slope was all about. So this was our rise, this was our run, and we defined it in terms of picking. So I always picked point number 2 with respect to point number 1. So the change in y was simply y2 minus y1 divided by x2 minus x1, and that gave us what the actual slope was. But what was the meaning? Well, the meaning and the relationship was all about rates of change. So how things are changing, okay, with respect to these variables. So for instance, I have written out here a lot of different examples. Most of the time, the rates of change are going to be with respect to time. There's no way around it. That's what we do, and you'll see many of these. In fact, the ones that I've written out here in black are all with respect to time. So for instance, you can have something like calorie burn. So what is calorie burn? Well, anyone who has worked out at any point in time, okay, will have a sense that you are burning calories. So possibly what you have is, this is a unit rate. So this would tell us that we have 15 calories burning for every single minute that passes by. So here is my, okay, variable, which is time. So that would go on the x-axis, okay? And then the variable energy, in this case, energy is measured in calories. That would go on the y-axis. And if you would plot this out, then we would simply have this as our rate, so this being our slope, and we could have an equation of y is equal to 15, okay, for every x. Now I can be very specific because here we are actually talking about energy. So this is energy equal to 15 calories per minute for every time, okay, that passes by. Now, if you were writing this out and if you would draw it out, then you would simply have a straight line going through 0, and every minute, okay, your energy would go from 15, then another 15 to 30, 45, 60, and so on. So we can plot this out, okay? So let me do that in decimals. There it is. So we have basically this concept, okay, of a slope, which relates back. So again, you have time on your x-axis, you have energy on your y-axis. I put here 15t because that is our slope, and then t, I restricted it, so it's greater than 0 because you're just a burning rate, so in terms of how much energy. And then I plotted the points for every basically minute as it goes by, And it should make sense to you that after 1 minute, okay, it would be 15. After 2 minutes, it's 30. After 3 minutes, it's 45, and so on. So when we are talking about these rates of change, it doesn't matter. I could have plugged in any of these. Please remember that they do have some relationship to real life when we are talking about our X, which is just a generalization of some quantity. Then our Y, so it's relating our X and our Y together one by one, and you can have all kinds of different rates. So here's a second one, speed, okay, of maybe a swimmer. It says 50 meters every 26 seconds. It's actually really fast. And we can make this a unit rate by dividing. So if I put 50 divided by 26, I would get 1.92, let's say 3. I'm going to just round it off, 1.923. What does this mean? That every second that passes by, that our swimmer is going to swim, almost 2 meters per every second. Now, one thing to please keep in mind, all of these are constant, so they're not changing. Is that reality? Not really. When you're burning calories, you're not always going to be burning 15 calories. It will depend on what you're doing, what your brain function is, if you're sick, if you're not sick, so on. So it's never a straight really line, okay? For speed, in terms of even a swimmer, they're not going to be, swimming exactly at this speed all the time. They might be able to do it for a certain amount of time, but the speed will fluctuate. The swimmers also make a turn whenever they're flipping, right? So then speed will change in that, okay? Maybe slow down, might speed up, okay? So you might have that. And you have all of these different rates, and you should understand these as you're walking into a calculus class. So things like a saving growth rate, for example, it says 2K, which means $2,000 every single month. So maybe somebody has a saving growth rate. That's what they want to put away in their banking account. There's a heart rate, which is, let's say, 63 beats per minute. So every single minute, our heart is beating at 63. That probably is a resting heart rate. And people's heart rates change. Volume flow, so 10 milliliters every single hour. Bit rate, okay, you may not know what that is, right? So 1 gigabits, okay, per second. So maybe in terms of processing, okay, of your computer, that's what you have. Now, they're not all with respect to time. You have things like, for example, gross domestic product per capita. This comes kind of from economics. And it's 72K, so 72,000 per every single person. I'm not going to go into the details. You don't have to necessarily know the definition. I just wanted to show you that your slopes, your rates, they're not always just with respect to time. They can be with respect to anything. Variable cost. So maybe for a manufacturer, it costs them $12 for every single item they make. Again, we can plot that out and we can see then the actual overall costs, okay, that manufacturer might have. But these are all unit, okay, rates. They're with respect to one particular thing, and we should understand these throughout. And we shouldn't have any issues. Now, when you're also walking in, okay, so I've mentioned here in terms of average rate of change, so what is this all about, okay, with respect, if we're doing something like this, you have to be very comfortable in being able to do this. It does relate back to our slope, right? So average rates of change is if you take on a function, okay, and you're given some function, we can define these particular secants basically at between two different points. So if I have a function, it doesn't matter what that function is. Let's say something that you're familiar with, maybe x squared. So this is just a quadratic, you know that it looks something like that. And we want to be able to find, the secant, okay, between 2 points. So that is the average, all right? So basically the average rate of change between these 2 points, it's nothing else but just the connection between them And here is your point number 1. Let's imagine that this is A1, and it is, so we can substitute it into our function. It's going to be f at A1. And then this would have been our point number 2. So this is nothing else but simply A. Let's say this is A2. And this would have been f at A2. We can find those. Now that we have 2 points, we can go back. We can find the slope of this particular line. And that would have been our average rate of change in that interval between A1 and A2. And once we have that, we can actually find out exactly what it is. So within here, so in fast forward fashion, this would have been our definition, okay, for this particular function on the interval between A1 and A2. That is our average rate. And our average rate of change is nothing else but simply a secant. So the secant is from here to here. And in order to define those secants, we can find the slope. We can actually find exactly what that particular line is. Okay, so that particular line, what we have, you have to be comfortable in doing that and understanding those secants. I have done this. Okay, so here, so just so that you can see it, there it is. Okay, so I have plotted this out. Now, so here's our secant. We can move these things around and we can find out exactly, what the slope is between these two. I have plotted it out all in here. Now, if you want to know how to do all of this, I did a video on that. Okay, so that's up above there. But the main idea for you as a student is to be able to understand what this secant is, how to find it, okay, for any given function if you're given 2 points. Now, the other last idea with regards to things that you have to be comfortable is, because once you have a secant, then you should slowly shift into the instantaneous rate of change, which now is talking about the tangent lines, which is going to be the key and pretty much the main idea within calculus that you're talking about, which is how do you find what the slope is at a particular point. And of course, you might say, I know how to do that because I have done it in functions where we have shifted, okay, and we've made our secant, okay, the 2 points come closer and closer and closer and closer together to finally, almost meet, and then it approximates the tangent at a particular point. So that is correct. That's what you want to do, but we want to be able to do that in a much easier fashion than just simply utilizing the secant, and that is where derivatives come into play. And that word of derivative is what you're going to be heading into as you're going throughout calculus. All right, so now instantaneous rate of change before I finish up this video. So it is nothing else in terms of a definition. So if you have a function at a particular point A, so what you want to be able to do is you want to have 2 points, as I said, as you would have for your secant, so your A1 and A2, but now they are very close together. You're going to have this H, so you're finding a slope in between point number A and a slight change where this H is basically as close to 0 as you possibly can make it. And we will see this notation quite often. It's going to bring about limits. So as H is approaching 0, what happens to this particular idea of our slope? And notice when you do this, the A and the A will cancel. So your definition of this, I'm going to duplicate it, bring it down a little bit. And of course, the a's will cancel, and it's going to be that. And that is the tangent line as h is approaching 0. And we can find that tangent line, which is being attached to a particular point. And then we are trying to find it at every single point on the function. What is that slope at a point which we call a tangent? That's the idea, that you want to be able to be comfortable with those items. So now, in terms of decimals and showing you, okay, this tangent line. So if I would go back in here, okay, of course, if I start bringing this thing in here, notice that that secant line is getting smaller and smaller. Now what I'm going to do is I'm going to remove my restrictions, so I am actually graphing, and notice this looks very much, as I bring this closer and closer, it looks like it's a tangent line at a particular point. And that's what we want to be able to do. So our idea, the entire thing, is that we want to be able to have it at just one point and then find it, the tangent, at any point we like, without necessarily doing the arithmetic of the slope for the tangent or for the instantaneous rate of change, okay, when it is happening at a particular point. So we want to be able to do this. That's what we want to be able to do. We want to be able to find this tangent at any point we like. We want to find the rate of change at any point for any function. So not just for x squared, you know, maybe for x cubed. Maybe we want to do that. So notice I can bring this in. Okay, and notice I can find this out. Maybe I want to be able to do it for sine functions. Same thing. We want to be able to find these points all the way along. And those are the instantaneous rates of change. That is the tangent at a particular point. And what we're going to be able to do is, how do we generalize it so that we can do it for any point on the given function? That's our ultimate goal in calculus, especially in the grade 12 calculus as you begin your studies. So to summarize it all, your idea of starting with calculus is to have a good understanding of slopes, knowing the dependent and independent variables, knowing that the rate of change is nothing else but simply a slope related to certain functions. You have studied in functions the average rate of change, which relates things back to a secant, and then the instantaneous rate of change, which relates things back to a tangent at a particular point. Be very comfortable in that, and from there we can start and talk about limits. See you in the future videos. Okay, welcome to calculus. Bye everybody.